Before we begin, please note that this presentation is for educational and informational purposes only. The concepts discussed are simplified to illustrate core principles and should not be taken as professional IT or network engineering advice. Always consult with a qualified professional for specific technical needs. In the single second it took me to say that over 100,000 gigabytes of data moved across the internet. That's the equivalent of streaming 30,000 high-definition movies. All at once. In 1 second. Every single day, the world sends over 350 billion emails, performs 8.5 billion Google searches, and ships nearly 40 million packages ordered online. We live our lives on a network that has become as essential as electricity and running water. Yet for most of us, it's a complete mystery. It's a magic cloud that just works, until it doesn't. Have you ever wondered what actually happens when you hit send on an email? Or when you type a website into your browser and press enter? How does that request from your laptop in Ohio find a single specific computer server sitting in a warehouse in Ireland in less than the blink of an eye? And how does it do that while navigating the storm of millions of other people's video calls, Netflix streams, and online games without ever getting lost? The answer is not magic. It's a system of engineering so brilliant, so vast, and so deeply embedded in our world that we've forgotten it's even there. And understanding it is no longer just for tech-savvy engineers. In our world, understanding the network is understanding power. It's understanding the economy, modern warfare, your personal privacy, and the future of human connection itself. This isn't just about routers and cables. It's about the fundamental nervous system of the 21st century. And over the course of this series, you are going to learn its language. I'm going to give you a mental model, a clear picture in your head, of how the entire digital world is connected, from the phone in your hand to a server halfway around the globe. By the end, you'll see the internet not as a cloud, but as what it really is, a breathtaking physical reality. To start, you have to forget everything you think you know. Forget about websites, emails, and videos. At its most basic level, the internet doesn't send any of those things. It only sends one thing: packets. Tiny, little digital envelopes. That's it. Everything you do online, every single thing, is first chopped up into thousands or even millions of these tiny packets. A text message might be 1 or 2 packets. An email could be a dozen. A single second of a 4K video you're streaming? That can be tens of thousands of them. Think of it like this. Imagine you wanted to mail the entire Encyclopedia Britannica to a friend across the country. You wouldn't try to stuff it into one giant building-sized mailbox. It's impossible. Instead, you would tear out every single page. On each page, you'd write a little bit of information. This is page 734 of Volume B. The full address of your friend, where it's going, and your return address so they know where it came from. Then you drop all 100,000 pages into the mail one by one. They would travel independently through the postal system, taking different routes, some arriving sooner than others. But because each page is numbered and addressed, your friend on the other end can reassemble them in the correct order, and voila, they have the complete encyclopedia. This is exactly how the internet works. Every packet is a digital page. It contains a small piece of the data you're sending, along with a header, the crucial addressing information. This header says where it's going, where it came from, and what number it is in the sequence. This single idea of breaking big things into tiny, individually addressed pieces is the bedrock principle that makes the entire modern world possible. It allows for incredible efficiency and resilience. If one packet gets lost in transit, a car crash on the digital highway, it's no big deal. The receiving computer just says, "Hey, I got packets 733 and 735, but I'm missing 734. Can you send that one again?" And the sending computer obliges. The whole system is built for an imperfect world. So let's trace the journey. Starts with your device, your laptop, your phone, your gaming console. Let's say you type a search into Google. Your computer takes that request, breaks it down into a few packets, and the first thing it does is hand them off to a piece of hardware called a network interface card, or NIC. This is the physical port or wireless chip in your device that acts as the departure gate. The packets are lined up, ready to go. But where to? They can't just scream out into the void. They need to go to the local traffic controller for your home. We all know what it's called, the router. Your Wi-Fi router is not the internet. It's the front door to the internet. Think of it as the mailroom for your house. Every device in your home, your phone, your smart TV, your laptop, is connected to this router. The router's first job is to be the local traffic cop, managing all the data flying around inside your own 4 walls. but its most important job is to act as the single gateway to the outside world. Now, for any of this to work, every device needs an address. You can't send a letter without a street address, and you can't send a data packet without a digital one. This is the famous IP address. The IP stands for Internet Protocol, which is just a fancy way of saying it's the set of rules for addressing and routing packets. Every single device connected to a network needs one. But here's a crucial distinction. The devices inside your house have private IP addresses, given to them by your router. Your laptop might be 192.168.1.5, and your phone might be 192.168.1.6. These addresses only matter inside your home network. They're like apartment numbers. If you send a letter to apartment 5B, the post office has no idea where to take it. They need the street address of the building first. Your router is what has the real street address, the public IP address. This is the one single unique address that the rest of the world sees. It's assigned to you by your internet service provider, or ISP. Think Comcast, Spectrum, AT&T. So when your laptop at its private address sends a packet to Google, it first goes to your router. The router then does something clever. It takes that packet, puts it in a new envelope, and writes its own public IP address in the return address spot before sending it out into the world. It's like the mailroom manager of your apartment building putting the building's main address on every piece of outgoing mail. That way, when Google sends a response, it knows which building to send it to. Your router then gets the mail and knows, this response is for the laptop in apartment 5B, and delivers it to the right device. So let's recap the journey so far. Your search query was broken into packets. Each packet was given a destination address, Google's IP address, and a return address, your router's public IP address. It traveled from your computer through the air via Wi-Fi to your router. Your router, the gateway of your home, has just forwarded it on. The packet has officially left your building. It's now in the hands of the first major player in the global network, your internet service provider. The ISP is the company you pay every month for internet access. They own the physical infrastructure, the fiber optic cables, the copper lines that run down your street and connect your neighborhood to the rest of the world. They are the on-ramp to the global information superhighway. Your tiny packet, carrying a piece of your search for cat videos, has just merged onto that on-ramp. But what happens next? How does it navigate a network of literally billions of interconnected devices to find one specific server thousands of miles away, in a fraction of a second? That journey across the sprawling, competitive, and brilliantly complex core of the internet is where the real story begins. To understand this journey, you first have to unlearn what you think the internet is. It's not a single, unified thing. It's not a cloud. It's a chaotic, breathtakingly complex agreement between tens of thousands of separate, independent, and often competing networks. Think of it less like a country with a national highway system, and more like a planet with thousands of independent kingdoms, each with its own road network. Some kingdoms are vast empires, others are tiny city-states. And the internet is the fragile, constantly renegotiated set of treaties that allows a message to travel from a small village in one kingdom, across the borders of a dozen others, to reach the capital of a distant empire. These kingdoms have a technical name: autonomous systems, or AS for short. An autonomous system is just a fancy term for a big network, or a collection of networks, that is managed by a single organization and has its own unified routing policy. Your home internet provider like Comcast or AT&T, they run a massive autonomous system. A tech giant like Google, Amazon, or Microsoft, they each have their own colossal globe-spanning AS, optimized to deliver their content as fast as humanly possible. Then you have the quiet giants, the companies you've probably never heard of like Lumen, Cogent, or Zayo. They are the backbone providers. They don't sell internet to you and me. They sell massive data transport services to other networks. They are the shipping lanes and freight lines of the digital world, the owners of the vast undersea fiber optic cables that connect the continents. So when you send a request from your laptop in Ohio on Comcast's network to a Google server in California, your data isn't traveling on the internet. It's starting its journey inside Comcast's autonomous system, and it needs to find a way to get into Google's autonomous system. In between those 2 points might be several other autonomous systems. This is the fundamental challenge of the internet's core. With nearly 100,000 of these independent networks all interconnected, how does your data packet know which way to turn at each intersection? There's no central map, no single all-knowing GPS. Instead, the internet relies on something that sounds more like gossip and rumor than high-tech engineering. It's a system built on trust and announcements, governed by a protocol called BGP, the Border Gateway Protocol. BGP is the official language of the Internet's kingdoms. It's what allows the routers at the borders of each autonomous system to talk to each other. These aren't your little home routers. These are monster machines, the size of refrigerators, processing trillions of bits per second. And all day, every day, they are gossiping. A router on the edge of Google's network is constantly shouting out to its neighbors, "Hey, I'm directly connected to all the IP addresses for YouTube, Gmail, and Google Search. The path through me is super short and fast." A router for a backbone provider like Lumen might announce, "I can reach Google, and I can also reach thousands of other networks in Europe and Asia." Each autonomous system advertises the destinations it can reach to its immediate neighbors. Those neighbors then take that information, add it to their own list of reachable destinations, and pass the updated list on to their neighbors. This ripple of announcements spreads across the entire internet in minutes. Every border router listens to the advertisements from all of its neighbors and uses them to build its own unique map of the internet. It's not a complete map of every single road, but more like a list of major highway exits. To get to this block of addresses, take the exit to AT&T. To get to that block, take the exit to Cogent. But here's where it gets interesting, and where the competitive part comes in. The router doesn't just pick the path with the fewest number of network hops. That's not how the world works. BGP decisions are driven by something far more powerful: money and business relationships. There are two main ways these giant networks connect: peering and transit. Peering is an agreement between two networks of roughly equal size to exchange traffic with each other for free. It's a handshake deal. Google and a massive ISP like Comcast might have a peering agreement. Google wants its YouTube videos to get to Comcast customers quickly, without paying a middleman. Comcast wants its customers to have a great YouTube experience, so they don't switch providers. So they agree to plug their networks directly into each other and exchange traffic without sending an invoice. It's mutually beneficial. Transit is what happens when the networks aren't equal. A small, regional internet provider in Montana can't just call up Google and demand a free peering arrangement. They don't have enough to offer. So instead, they pay a larger backbone network, a Tier 1 provider, for transit. They are paying for the privilege of using that larger network's connections to reach the entire rest of the internet. They are a customer. These business deals are the secret sauce that dictates how your data flows. A router's BGP decision process is a complex algorithm that looks something like this. First, is there a direct connection to the destination? No. Okay, second, is there a path through a network we have a free peering agreement with? Yes. Great, send it that way. It's free. If not, okay, which of our paid transit providers offers a path? Let's use the cheapest one that meets our performance standards. The shortest path might be the most expensive, so the BGP-speaking routers will actively avoid it, sending your data on a longer, more convoluted journey to save the company a fraction of a cent. This all happens in the real world, in massive, nondescript buildings you've driven past 1,000 times without a second look. These are Internet Exchange Points, or IXPs. An IXP is like a grand digital bazaar. It's a neutral territory, a data center where hundreds of different autonomous systems all bring their routers and plug them into a massive, shared network switch. It's in these buildings that a router from Netflix can be physically plugged into a port right next to a router from Verizon, allowing them to form a peering relationship and exchange terabits of movie data directly. Ashburn, Virginia, is famous for being one of the densest concentrations of these data centers on the planet. So much of the world's internet traffic flows through this one suburban town that it's often called Data Center Alley. So let's rerun our journey. You click a link. Your request is bundled into a packet. It leaves your house and travels to a router at the edge of your ISP's autonomous system. That router checks its BGP-derived map. It sees the destination as a Google IP address. The router knows, based on constantly updated advertisements, that it has a peering agreement with Google at the Equinix IXP in Chicago. That's the cheapest and therefore best path. It fires your packet out of its port that connects to the fiber optic line running to Chicago. The packet arrives at the IXP, crosses the switch, and enters Google's autonomous system. From there, Google's internal network takes over, whisking it to the right server. The whole round trip, a journey dictated by Byzantine business deals and router gossip, happens in less time than it takes you to blink. It's an incredible system, a decentralized, resilient, global network built not by a single architect, but by the emergent, self-interested behavior of thousands of independent entities. But this entire global edifice is built on a foundation of trust. The whole system works because it assumes that the routing advertisements being shouted across the internet are honest. It trusts that when an autonomous system says, "I have the best path to YouTube," it's telling the truth. But what if it isn't? What happens if a network starts lying? What if someone in a small, obscure network in another country suddenly starts advertising to the world that they are Google, or that they own the IP addresses for your bank? In a system built on gossip, what happens when the rumors are malicious, and the routers of the world are tricked into sending the planet's data down a dark alley? This is called a BGP hijack, and it's the digital equivalent of changing all the road signs in a country to point to your house. It works because the entire system, this global gossip network of routers, was built on a single flawed premise: trust. BGP was designed in the 1980s, a more academic and collaborative era of the internet. It was a gentleman's agreement. When a router from a major telecom announced, "I have the path to these addresses," all the other routers just believed it. There was no built-in mechanism to verify if that router was telling the truth. No cryptographic signature, no digital passport check. A router in Moscow could announce it had the best path to the Pentagon, and every other router would simply say, "Okay, thanks for the update," and dutifully start sending Pentagon-bound traffic to Moscow. The internet's global positioning system is based on the honor system. And in the modern world, that's a terrifying vulnerability. So how does a heist like this actually work? An attacker, controlling their own autonomous system, even a small, insignificant one, starts making a very specific, very loud announcement. They don't just say, "I have a route to Google." That's too broad, and the real Google's announcement would be more credible. Instead, they lie with precision. They announce a more specific route. Imagine Google's real network announces to the world, "I own this huge block of 1 million IP addresses." The attacker then shouts, "Well, I own this tiny block of 256 addresses that just so happens to be inside Google's block, and it contains their main servers." In the world of BGP, specificity is king. The routers of the world see this new, more detailed route and think, "Ah, a shortcut." They prioritize the more specific path. The malicious rumor spreads like wildfire across the internet's backbone. Within minutes, a significant portion of the world's internet traffic destined for Google is diverted, flowing not to Google's massive data centers, but to the attacker's servers. The data has been led down that dark alley. Once the traffic is theirs, the attacker has options, all of them bad. They can create a digital black hole, simply dropping all the packets. To the outside world, Google has vanished. This is a denial of service attack on a planetary scale. Or they can perform something far more sinister: a man-in-the-middle attack. They can quietly intercept the data, copy it, inspect it for passwords, financial information, or state secrets, and then forward it along to the real Google. The user might experience a slight delay, a little lag, but they'd be none the wiser. Their data has been siphoned off, and the connection completes as normal. It's the perfect crime. This isn't just a theoretical threat. It has happened with catastrophic and sometimes bizarre consequences. February 24, 2008. The government of Pakistan issues an order to its national telecom provider: block access to YouTube nationwide. The engineers at Pakistan Telecom decided the quickest way to do this was to create a null route, an internal black hole, for YouTube's IP addresses. For anyone inside Pakistan, YouTube would simply cease to exist. But then, one of those engineers made a catastrophic mistake. They didn't just create this black hole route internally, they accidentally announced it to the rest of the world via BGP. Suddenly, Pakistan Telecom, a relatively small player on the global stage, was screaming to the world's largest internet carriers that it had the best, most specific path to YouTube. And the world's routers, following their programming, believed them. First, a major carrier in Hong Kong updated its tables. Then all of its partners did. The lie spread from Asia to Europe to North America. Within 2 hours, Pakistan Telecom, in an attempt to block YouTube for its own 170 million citizens, had accidentally black-holed YouTube for a majority of the planet's 2 billion internet users. YouTube's own engineers were mystified. Their servers were up, their networks were fine, but the traffic had simply stopped. It took a global scramble of network operators, making phone calls in the middle of the night, to manually filter out Pakistan's false announcement and restore order. It was a powerful accidental demonstration of how fragile the internet's core routing system truly is. But what happens when the hijack isn't an accident? April 24, 2018. For about 2 hours, users trying to access myetherwallet.com, a popular service for managing cryptocurrency, were being strangely redirected. The site they landed on looked identical. The login page was perfect, but it was a sham, a sophisticated phishing site hosted on Russian servers. The attackers weren't hacking the website itself. They were hacking the internet's address book. They executed a BGP hijack, specifically targeting the IP addresses for Amazon's DNS service, Route 53, which MyEtherWallet used. By announcing a more specific route for Amazon servers, they tricked a portion of the internet into sending its DNS queries to them instead. When a user typed in myetherwallet.com, the hijacked DNS server gave them the IP address of the fake phishing site, not the real one. Unsuspecting users logged in, and the attackers harvested their credentials, draining their crypto wallets. They stole over $150,000 in a matter of hours. This wasn't a clumsy brute force attack. It was an elegant, insidious manipulation of the internet's fundamental trust. They didn't break down the door to the bank. They just changed the street sign so everyone drove to their fake bank instead. These hijacks can be even more subtle, more targeted. For years, security researchers have observed suspicious, short-lived rerouting of internet traffic. In 2017, traffic for major financial institutions like Visa, MasterCard, and others was inexplicably rerouted through a Russian state-controlled telecom for a few minutes at a time. The duration was too short to cause a noticeable outage, but it was just long enough to be intercepted, copied, and analyzed. It bore all the hallmarks of state-sponsored espionage, using the inherent weakness of BGP as a tool for global intelligence gathering. Fixing a hijack is a messy, frantic, and deeply human process. There is no global kill switch. It's a mad scramble. Engineers at the victim's company get on secure chat channels and emergency phone bridges with engineers at the major internet backbone providers, the Tier 1 networks. They have to prove they are the legitimate owners of the IP addresses and convince the other networks to manually ignore the fraudulent announcements from the rogue AS. It's an exercise in persuasion, reputation, and sheer panic. They are essentially trying to shout louder and more convincingly than the attacker, hoping the rest of the network listens to them first. We have built our entire modern society, our commerce, our communication, our governments, on top of a system that was designed in the 1980s and runs on a digital handshake. This foundation of trust, once a feature, is now the internet's most glaring bug. It's clear that in an age of cyber warfare, digital pirates, and nation-state hackers, a gentleman's agreement is no longer enough. The honor system has failed. So the question becomes a monumental one. How do you bolt a cryptographic lock onto the very foundation of the internet while it's being used by all 5 billion of us? How do you change the engines on a 747 while it's in mid-flight? The answer, it turns out, is not with a single elegant solution, but with a slow, messy, and monumentally complex global upgrade. It's a project so ambitious it's almost invisible. A digital fortification built brick by painstaking brick, right under our feet. The name of this project is DNSEC, the Domain Name System Security Extensions. And it's less like changing an engine and more like teaching the plane how to build its own armor while flying through a meteor shower. To understand how it works, let's go back to our phone book analogy. The original DNS was like a phone book anyone could scribble in. DNSEC gives the phone book an authenticity check. Imagine you wanted to be absolutely sure you had the real official phone number for the White House. What if, next to the entry, there was an undeniable, unforgeable signature from the president himself? A signature so unique and complex that it's mathematically impossible to fake, but incredibly easy for anyone to verify as genuine. That's what DNSEC does, but with cryptography. It adds a digital signature to DNS records. When your computer asks for the IP address of, say, mybank.com, the server doesn't just send back the numbers. It sends back the numbers and a cryptographic signature. This signature essentially says, I, the official authoritative server for mybank.com, solemnly swear that this is the correct IP address, and here is my unforgeable seal to prove it. Your computer, or more accurately, the resolver it's talking to, can then check that signature. It performs a quick mathematical calculation, and if the signature is valid, it knows the information hasn't been tampered with. It knows it hasn't been lied to by some criminal sitting in a coffee shop or a compromised router. If the signature is missing, or if it's a forgery, your computer can sound the alarm and refuse to connect, protecting you from being sent to a fraudulent website. But this raises an immediate, critical question. How does your computer know what the real signature is supposed to look like? If a hacker can intercept the DNS request, couldn't they just invent a fake signature and tell your computer, Hey, this is the official signature, trust me. This is where the true genius and the staggering complexity of the system comes into play. It's called the chain of trust. Think of it like a pyramid of authority. You don't have to know and trust the signature of every single website on the planet. That would be impossible. Instead, you only have to trust a handful of sources at the very, very top. It works like this. The server for mybank.com has its signature vouched for by the servers that manage all .com domains. The .com servers, in turn, have their signature vouched for by an even higher authority. This continues all the way up the chain until you reach the absolute peak of the pyramid, the DNS root zone. The root zone is the master phone book for the entire internet. It doesn't know where mybank.com is, but it knows where to find the official phone book for all the .com addresses. It knows where to find the phone book for .org, .gov, and every other top-level domain. And this root zone is protected by the most powerful digital key on the planet. This is the ultimate source of trust for the entire system. If you can trust the signature of the root, you can follow the chain of verified signatures all the way down to the website you want to visit. Each level validates the level below it. The root validates .com validates mybank.com. So the entire security of this global system hinges on one thing: the absolute, unquestionable integrity of the key that signs the root zone. The master key to the internet's directory. And the story of how that key is protected is something straight out of a Hollywood thriller. Because this key is so powerful, it can't be stored on a computer connected to the internet. It can't be held by one person or one company, or even one country. The trust has to be global. So, a group of individuals from all over the world were selected. They are academics, engineers, and security experts, crypto officers chosen to represent the global internet community. Several times a year, these individuals travel to one of two highly secure data centers, one in Virginia and one in California. To get inside, they pass through a series of man-traps and doors secured with PIN codes, key cards, and biometric scanners. The room itself is a steel cage, isolated from all electronic eavesdropping, constantly monitored by cameras and motion detectors. Inside that cage is a safe. Inside that safe are several other safes. And inside one of those is the hardware security module, a small tamper-proof computer that holds the master key. This device is designed to be so secure that if someone tries to physically break into it, it will destroy the key it holds. But no single person can activate it. The process requires multiple key holders to be present. Each one has a physical smart card containing a piece of the activation key. They also have a physical metal key to a safe deposit box that contains the smart card. Everything is redundant. Everything is witnessed. The entire event, known as the root key signing ceremony, is scripted down to the second, live-streamed and audited. The participants present their keys, unlock the safes, insert their cards, and in a carefully choreographed sequence, they use the master key to generate the digital signatures that will secure the internet's root zone for the next few months. This is what it took. This is the changing the engines mid-flight. It required creating a system of ultimate trust, not based in code alone, but in a physical human ceremony. It required convincing thousands of independent network operators, from giant ISPs to small businesses all over the world, to upgrade their systems, to voluntarily adopt this new, more complex standard. It had to be rolled out slowly, carefully, over years, ensuring that older systems that didn't understand DNSSEC wouldn't simply break. It was a decade-long effort of engineering, diplomacy, and collaboration on a scale the world has rarely seen. And what does it all mean for you? It means that today, when you type an address into your browser, there is an invisible chain of cryptographic trust, anchored by a physical ceremony in a steel cage, that works to ensure the address you get back is the one you actually asked for. It's the system that stops an entire category of invisible attacks that could redirect you from your bank's real website to a perfect replica designed to steal your password. It's a silent guardian, a lock bolted onto the foundation of the internet. We solved the address problem. We now have a system to verify that the address on the envelope is correct, that it hasn't been erased and rewritten by a malicious mailman. But there's another, equally massive problem. The system proves you've sent your letter to the right building. But what if the letter itself is written on a postcard? What if anyone, at any point along the mail route, can simply read everything you've written? Verifying the destination is only half the battle. The conversation itself, the data flowing back and forth between you and the server, is still completely exposed. How do we put that postcard inside a locked, armored briefcase? The answer is cryptography, the art of secret writing. It's a science that's as old as empires, used by Caesar to send coded messages to his generals, and by spies to pass secrets in the dead of night. But today, it's not just for spies and generals. It's for you every single time you log into your email, buy something online, or send a private message. It's the invisible armor of the digital world. That postcard, your raw, readable data, is what we call an HTTP request. Hypertext Transfer Protocol is the standard way computers used to talk. But HTTP is a gossip. Speaks out loud. Anyone sitting between your computer and the server can overhear everything. The person running the Wi-Fi at your local coffee shop, they can see it. Your internet service provider, they can see it. A malicious actor who has managed to tap into the line somewhere, they can absolutely see it. Your password, your credit card number, your embarrassing search history. All written on a postcard for the world to read. This is where the armored briefcase comes in. We add one letter to HTTP, an S, for secure. HTTPS. When you see that little padlock icon next to the address bar in your browser, you're looking at the digital equivalent of a vault door. But how does it work? How do two computers who have never met before agree on a secret code without anyone else listening in? If you shout the secret code across the room, everyone hears it. If you send the key to the briefcase in a separate, unlocked envelope, a thief can just grab that envelope, open the briefcase, and you're back to square one. This is one of the most brilliant and fundamental problems of modern computing. And the solution is a breathtakingly clever piece of mathematical magic called asymmetric cryptography, or public key cryptography. Imagine you have a very special kind of padlock. This padlock is unique. You can create an infinite number of copies of the padlock itself, and you can give these open padlocks to anyone in the world. Anyone can take one of your padlocks, put something in a box, and snap the padlock shut. But here's the magic part. There is only one key in the entire universe that can open that padlock. A single solitary key. And you keep that key. You protect it with your life. The open padlock is your public key. The one-of-a-kind key is your private key. Now let's go back to you trying to connect to your bank. Your browser reaches out to the bank server and says, "Hey, I want to talk, but I want to talk securely." The bank server responds, "Great. Here is my official ID, that certificate we talked about last time, and here is a copy of my open padlock, my public key." Your browser first looks at the ID, the certificate, and checks with the trusted authority to make sure it's really the bank. Once it's confirmed, your browser knows the padlock it just received genuinely belongs to the bank. Now your browser needs to establish a secret for this specific conversation. It generates a brand new temporary secret key. Let's call this the session key. This is the key you'll actually use to scramble and unscramble the real data, like your account information. But how do you get this new session key to the bank without anyone else seeing it? You use their padlock. Your browser takes the brand new session key, places it inside a digital box, and snaps the bank's public padlock onto it. It then sends this locked box across the internet to the bank. Now think about what's happening. That box is flying through all those different routers and servers. Anyone can see the box. They can grab it, look at it, but they can't open it. They don't have the key. The only entity in the world that can open that padlock is the one holding the corresponding private key, the bank server. The bank server receives the locked box, uses its secret private key to open it, and out comes the session key that your browser created. And just like that, the magic has happened. Both you and the bank now share a secret, the session key, that was never transmitted openly across the internet. This initial elegant exchange is called the TLS handshake. Transport layer security. It's the digital secret handshake that secures the modern world. But why go through all that trouble with the complicated padlock and key system, just to agree on a simpler key? Why not just use the public and private keys for everything? The answer is speed. Asymmetric cryptography, the public/private key system, is incredibly powerful for establishing a secret, but it's mathematically intensive. It's slow. Trying to encrypt and decrypt a whole movie or even a high-resolution photo with it would be painfully inefficient. The session key, however, is used for what's called symmetric cryptography. This is more like a traditional lockbox, where the same key is used to both lock and unlock it. It is thousands of times faster and more efficient for encrypting large amounts of data. So the public/private key system is used for one thing and one thing only, to securely deliver the real key, the session key, that will be used for the rest of the conversation. It's like using a super secure armored truck just to deliver the keys to a high-speed Ferrari. You don't use the truck for the whole race, You use it to make sure the right person gets the keys to the fast car. From that moment on, every piece of data that flows between your browser and the bank server, your login, your password, the amount you want to transfer, your account balance, is scrambled using that shared symmetric session key. The postcard is now inside the armored briefcase, locked with a key that only you and the bank possess. Even if someone intercepts the briefcase, all they'll see is gibberish, a chaotic stream of unreadable characters. They have the message, but they don't have the cipher. This entire process, from the initial hello to the agreement on a shared secret key, happens in a fraction of a second. It happens every time you see HTTPS, every time you log in to a social media account, every time you make a purchase on Amazon. It is the silent, unsung hero of the internet. Without it, e-commerce would be impossible. Online banking would be a fantasy. Private communication would be a contradiction in terms. The entire foundation of trust that allows our digital society to function would crumble. We've managed to turn a public square into a private room. We've taken a message that anyone could read and locked it in a vault that only the intended recipient can open. We have security. We have privacy. The connection is sealed. So we have our locked armored briefcase. And thanks to DNS, we know the exact street address to send it to. We've done everything right. Our message is secure, and its destination is verified. But the internet isn't a single straight road. It's a mind-bogglingly complex, ever-changing labyrinth of billions of pathways, intersections, and interchanges, all run by different companies and organizations. It's less like a highway and more like a living organism. So we've locked the message and addressed the envelope. But what happens when we drop it into the mailbox? Who are the mail carriers of the digital world? And how do they prevent our data from getting lost in a city with a billion streets? The digital mail carriers are called routers, and the city with a billion streets is the internet itself. These two things, the carriers and the city, are what make it possible to send a message from your couch in Ohio to a server in a Tokyo data center in less time than it takes you to blink. It's a system of such staggering complexity and speed that it feels like magic. But it's not magic. It's routing. When you hit send on an email or click a link, your computer bundles your data into those packets we discussed, each one a sealed and addressed envelope. The first stop on its journey isn't some massive internet exchange. It's that humble box with the blinking lights in your living room, your home router. Now, your home router is a clever little device that wears two hats. Inside your home, it acts like a local mail sorter for your own private street. This is called a local area network, or LAN. Let's say you want to print a document. Your computer sends a packet addressed to your printer. Your router, acting as a device called a switch, looks at the packet, but it doesn't care about the final destination IP address out on the internet. Instead, it looks at a different, more local address called a MAC address. Think of it this way. The IP address is like your home street address, which anyone in the world can use to send you a letter. The MAC address is like the name of the person living in the house. It's a unique physical identifier burned into every network-capable device on Earth. When you're sending mail just to someone else in your own house, you don't need the street address. You just put their name on it. Your router does the same thing. It keeps a little list of all the devices in your house and their MAC addresses. It sees the packet is for the printer, and it delivers it directly right there on your local network. No need to involve the global postal service. But what happens when you click on a YouTube video? The destination IP address on that packet isn't in your house. It's somewhere far away, at one of Google's data centers. Now your router switches hats. It stops being a local mail sorter and becomes an on-ramp to the superhighway. It looks at the destination IP address and says, "Nope, not on my street." It knows it has only one way to send mail to the outside world, through your internet service provider or ISP, Comcast, Verizon, AT&T, whoever you pay each month. So it forwards your packet out of your home and into the vast interconnected network of your ISP. This is the moment your data packet leaves home and begins its real journey. It arrives at the first major intersection, a powerful industrial-grade router at your ISP. This router is nothing like your home device. It's a supercomputer dedicated to one task, directing traffic. And it makes its decisions by consulting something called a routing table. A routing table is essentially the internet's GPS. It doesn't have a map of the entire world's internet. That would be impossibly large and constantly changing. Instead, it has a much simpler set of instructions, like a series of signposts at a highway intersection. One sign might say networks A through F go this way. Another might say networks G through M go that way. And a final one might say, for everything else, send it to that big router over there. This router looks at your packet's destination IP address, the address for YouTube's server. It consults its routing table and determines the most efficient next hop to get that packet closer to its destination. It doesn't know the full path. It only needs to know the very next step. So it flings your packet across a high-speed fiber optic cable to the next router in the chain. This process repeats over and over at astonishing speed. Hop after hop after hop. Your packet might travel from your local ISP office to a major regional hub in a city like Chicago or Dallas, then get handed off to what's called a Tier 1 network provider, one of the massive companies that own the long-haul fiber optic backbones that cross countries and oceans. At each hop, a router makes an independent decision in a fraction of a millisecond. It's a decentralized system of pure efficiency. And this is where the true genius of the internet's design becomes clear. What if one of those fiber optic cables gets cut by a construction crew? What if a router in Denver overheats and fails? On a traditional phone call from the old days, that would be it. The connection would be broken. A single point of failure would kill the whole thing. But the internet was designed by the military to survive a catastrophe. It has no single point of failure. The routers are constantly talking to each other, using special protocols like the Border Gateway Protocol or BGP. You can think of BGP as a global traffic update service for the internet. When that router in Denver fails, its neighboring routers immediately notice it's gone. They broadcast a message to all their peers. Hey, the road through Denver is closed. Update your maps. Almost instantly, thousands of routers around the world update their routing tables. They erase the path through the broken router and calculate the next best alternative. So when your next packet arrives at that intersection, instead of being sent toward the dead end in Denver, it's rerouted, maybe through Salt Lake City or Kansas City, without you ever noticing a thing. The network heals itself in real time. This dynamic rerouting is happening millions of times a second, all over the globe, making the internet a resilient living web, rather than a rigid, brittle structure. So your tiny packet, having survived its journey across this chaotic and self-healing network, finally arrives at the edge of its destination, Google's network. The final internet router hands the packet off to Google's own internal routers. This is like the global postal service handing a letter over to the internal mailroom of a massive corporate campus. Once inside, the process flips in reverse. A Google router sees the packet is for a specific server in a specific rack in a massive warehouse-sized data center. It sends the packet into that data center's local network. Here, the big routers step aside and the local delivery experts, the switches, take over. Just like in your house, the switch reads the final MAC address and delivers the packet to the exact physical port on the exact server that is waiting to host the cat video you requested. The entire journey from your laptop through a dozen routers across the country to a specific server in a data center might have taken just 30 or 40 milliseconds. In that time, a complex and beautiful dance of addressing, switching, and routing has taken place. Thousands of devices have collaborated, each playing its tiny part, consulting their maps, and making split-second decisions to guide your request across a global mesh of glass and light. We have successfully navigated the physical labyrinth. We've followed the packet from its origin to its destination, through local streets and across continental highways. But the journey isn't over. The packet has arrived, but what does it say? How does the server know if this packet is part of a request for a web page, a piece of an email, or a frame of a video stream? Delivering the letter is one thing. Understanding the language it's written in is another challenge entirely. This is where the magic of the transport layer comes in. Think of the server's IP address not as a house, but as a massive skyscraper, a giant corporate headquarters. Sending a packet to just the IP address is like sending a letter to 123 Main Street, Megacorp Tower. The mailroom clerk gets it, but who does it go to? Accounting? Legal? The CEO on the penthouse floor? It's chaos. To solve this, every letter needs not just the street address, but a specific suite number or department name. In the world of networking, these suite numbers are called ports. A port is just a number, from 1 to 65,535, that acts as a specific endpoint within a computer. When your computer sends a request to a web server, it doesn't just send it to the server's IP address. It sends it to the server's IP address at port 443. Why 443? Because that's the universally agreed upon suite number for secure web traffic, the HTTPS protocol you see in your browser bar. If you were sending an email, your computer would likely send the packet to port 25 or 587 on the mail server. It's a beautifully simple system. The server's operating system acts as the mailroom clerk. It sees an incoming packet, looks at the destination port number and says, "Ah, this one is for port 443, that goes to the web server application. This other one is for port 25, that goes to the email server application." Just like that, the chaos is resolved. We now have a way to deliver data not just from one computer to another, but from a specific application on your computer like your Chrome browser, to a specific application on the server like its Apache web server. This application-to-application communication is the core job of the transport layer. But this layer does more than just play mailroom clerk. It also has to decide how the message gets delivered. And for this, it employs two very different kinds of messengers, with two completely opposite philosophies. Their names are TCP and UDP. Let's start with the most famous of the two, TCP, the Transmission Control Protocol. TCP is the meticulous, reliable, slightly obsessive-compulsive courier. It believes that every single piece of data is sacred. Losing a single bit is unacceptable. When your browser wants to get a web page from a server, it uses TCP. And the first thing TCP does is not send the data. No, that would be reckless. First, it makes a phone call. This is called the three-way handshake. Your computer sends a small packet, a SYN packet, which is like saying, "Hello, server at port 443. Are you there, and are you ready to receive some data?" The server, if it's listening, responds with its own packet, a SYN packet, which means, "Yes, I'm here and I'm ready. I acknowledge your request to connect." Finally, your computer sends one last packet, an ACK packet saying, "Excellent. I acknowledge your acknowledgement." The connection is now established. It's a formal, polite opening to a conversation. Only after this handshake is complete will any actual data, like the request for the web page, be sent. But TCP's obsession with reliability doesn't stop there. It takes the data for the web page, which is far too large to fit in a single packet, and chops it up into thousands of smaller, numbered segments. It's like taking a 1,000-page book, tearing out each page, and putting each page into its own numbered envelope. As the server sends these packets, your computer receives them. For every few packets it receives, it sends back an acknowledgement like, "Got packets 1 through 10, thanks." This lets the server know everything is arriving safely. Now, what happens if packet number 11 gets lost in the internet wilderness? Maybe a router got congested and dropped it. Your computer will receive 10 and then 12. It will immediately notice the gap. It will then send a message back to the server saying, "Hey, I got 10 and 12, but I'm missing packet 11. Can you please send that one again?" The server then retransmits only the missing packet. And what if the packets arrive out of order? Say 13 arrives before 12. No problem. Because every packet is numbered, your computer's TCP software can simply reassemble them in the correct sequence, like putting the pages of the book back in order, before handing the complete, perfect web page data to your browser. This is why when you load a web page, you never see a garbled mess of text or a half-loaded image. TCP guarantees it. It's the protocol of perfection. It's used for web browsing, email, file transfers, anything where 100% data integrity is non-negotiable. But what if perfection isn't what you need? What if what you really truly need is speed? This is where our second messenger comes in. Its name is UDP, the User Datagram Protocol. If TCP is the certified mail courier who requires a signature and tracks every step, UDP is the guy who just flings a postcard over the fence and hopes for the best. UDP is the polar opposite of TCP. It is fast, lightweight, and completely unapologetic about it. UDP is what we call connectionless. There is no three-way handshake. There's no "Hello, are you there?" UDP just takes the data, sticks it in a packet, and fires it off. It doesn't number the packets. It doesn't wait for acknowledgements. It doesn't care if the packet arrives, if it arrives out of order, or if it arrives at all. It just sends. Its philosophy is fire and forget. Now, you might be thinking, why on earth would we ever use something so reckless? The answer is in the applications that need it. Think about a live video call, or streaming a live sports game, or playing a fast-paced online game. In these situations, what's more important? Getting every single frame of video perfectly, or getting the video right now? If you're on a video call and a single packet containing a tiny fraction of a second of video gets lost, what would you rather happen? Would you rather the entire video stream freeze for 2 seconds while TCP meticulously requests a retransmission of the lost packet? Or would you rather just have a tiny momentary pixelated glitch and have the stream continue in real time? For most people, the answer is obvious. A tiny glitch is acceptable. A long freeze is infuriating. Speed and low latency are more important than absolute perfection. That's the genius of UDP. It's built for applications where a small amount of data loss is a perfectly acceptable trade-off for maintaining a constant, real-time flow. Online gaming is another perfect example. Your computer is sending your position and actions to the game server dozens of times per second. If one of those packets gets lost, who cares? A new one with your updated position will arrive a few milliseconds later. Using TCP would be a disaster, causing lag and stuttering as the game waits for retransmissions of old, irrelevant position data. UDP powers much of the real-time internet we love. Live streaming, online gaming, voice-over IP calls like Skype or Discord, and even the DNS system that looks up website addresses, which needs to be lightning fast. So we have two tools for the job: TCP for reliability, UDP for speed. The application developer gets to choose which one makes sense. And this entire system of communication hinges on that simple combination we talked about: an IP address and a port number. This combination is so fundamental it has its own name: a socket. A socket is one specific endpoint of a two-way communication link between two programs on the network. When your browser connects to Google, it creates a socket on your computer and connects to a socket on Google's server. A specific IP address and a specific port number, using a specific protocol like TCP. We've now built a remarkable system. We can send data across the world from one specific application to another, and we can even choose whether we want that delivery to be perfectly reliable or blazingly fast. The connection is made. The packets are flowing. But we've only talked about the packaging and the delivery instructions. We haven't talked about the actual conversation itself. Once that TCP connection is established and stable, how do your browser and the server manage their dialogue? How do you log into your bank's website and stay logged in as you click from your checking account to your savings account? The connection is just the beginning. Managing the session, the ongoing conversation, is a whole new layer of complexity. The answer is a deceptively simple, yet brilliant digital trick: the cookie. And no, not the kind you eat. This is about a small text file, a tiny digital breadcrumb that solves one of the biggest paradoxes of the internet. You see, the fundamental protocol that powers the web, HTTP, is what we call stateless. This is a critical concept. Being stateless means that every single request your computer makes to a server is treated as a brand new, isolated event. The server has no memory of who you are, or what you did a millisecond ago. Imagine trying to have a conversation with someone who has no short-term memory. You say, "Hello, my name is Alex." They reply, "Nice to meet you." Then you ask, "What's the weather like?" And they respond, "I'm sorry, who are you?" That's HTTP. Every time you click a link, load a new page, or add an item to your cart, you're essentially reintroducing yourself to a server that has already forgotten you. So how on earth do you stay logged into your bank? How does Amazon remember what's in your shopping cart as you browse for 20 minutes? This is where the cookie comes in. It's the web's version of a memory aid. Let's stick with the bank example. When you first enter your username and password and click Login, you send that information to the bank server. The server checks its records, confirms you are who you say you are, and says, "Okay, you're authenticated." But instead of just sending you to your account page, it does something clever. It generates a unique, random, long string of characters. Think of it as a temporary secret key. This is your session ID. The server then stores this ID in its own database, linking it to your account details. This key, the server notes, belongs to Alex, who is now logged in. Then it sends that session ID back to your browser, packaged inside a cookie. Your browser, without you even noticing, catches this cookie and stores it. Now, you have a digital token, a proof of your current authenticated session. From this point forward, for every single click you make on that website, checking your balance, viewing transactions, making a transfer, your browser automatically attaches that cookie to the outgoing request. It's like wearing a VIP wristband at a concert. You don't have to show your ticket at every single checkpoint. The security guard just glances at your wrist and waves you through. When the bank server receives your next request, the first thing it does is look for that cookie. Finds it, reads the session ID, and instantly looks it up in its database. "Ah," it says. "The wristband with number 9-754. That's Alex. He's already logged in. He wants to see his savings account." The server then serves up the correct page. and the illusion of a continuous, ongoing conversation is perfectly maintained. You never had to log in again. The stateless protocol has been given a stateful memory. The best analogy for this is a coat check at a fancy event. When you arrive, you hand over your coat, your authentication details, your username and password. The attendant doesn't try to memorize your face. Instead, they hang up your coat and give you a small plastic ticket with a number on it. That ticket is your cookie. The ticket itself has no value. It doesn't contain your name or your credit card number. It's just a dumb token, a pointer. But it's uniquely linked to your valuable coat, which is stored securely behind the counter, on the server. As you enjoy the party, you keep that ticket in your pocket. If you need to go back to the coat check for any reason, you don't reintroduce yourself. You just show them the ticket. They see the number, go to the corresponding hook, and retrieve your coat. This is exactly how session management works. The cookie in your browser is the ticket. The server is the coat check room, carefully managing thousands of coats, each linked to a unique ticket number. This entire elegant dance of requests, responses, and cookies happens at the very top of our networking model, layer 7, the application layer. This is the layer we, as users, interact with most directly. It's not about the physical wires or the routing of packets anymore. It's about the applications themselves, your web browser, your email client, your video game, and the protocols they use to communicate. HTTP, which we've been discussing, is the king of the application layer. But it has company. When you send an email, your mail client is likely using SMTP, the Simple Mail Transfer Protocol. When you transfer files to a server, you might use FTP, the File Transfer Protocol. Each of these is a specialized language designed for a specific type of application-to-application conversation. This layer is where the data finally takes on a form we can understand. It's no longer just a stream of ones and zeros. It's a web page, an email, a video stream. It's the reason the whole network exists in the first place, to allow our applications to talk to each other and deliver meaningful content to us. But this system of tickets and coat checks also introduces a new kind of vulnerability. What happens if someone steals your coat check ticket? They can walk up to the counter, present the ticket, and walk away with your coat. The same is true for your session cookie. If a malicious actor can somehow intercept or steal that cookie from your browser, a technique known as session hijacking, they can present it to the bank server. The server, seeing a valid session ID, has no reason to believe it isn't you. It will grant the attacker full access to your logged-in session. This is why the security of that connection is paramount. This is why HTTPS, the secure version of HTTP we talked about earlier, is so critical. By encrypting the entire channel between your browser and the server, HTTPS ensures that even if someone is snooping on the line, the cookie, your session ticket, is just unintelligible gibberish to them. It keeps your digital coat check ticket safe from prying eyes. So this intricate system of session management is the invisible engine behind almost every interactive experience you have online. It's how a news site remembers you prefer dark mode. It's how a streaming service knows what episode you're on. It's how an e-commerce giant keeps your meticulously curated shopping cart intact for days. It's the ghost in the machine, providing memory to the memoryless, and turning a series of disconnected shouts into a coherent, personal conversation. We've now seen how two computers find each other across the globe using IP addresses, how they establish a reliable connection using TCP, and how applications manage an ongoing conversation using HTTP and cookies. We've covered the what, the where, and the how, but there's a crucial first step we've glossed over. When you type google.com into your browser, how does your computer know that it needs to talk to the server at IP address 172.217.14.238? We don't navigate the internet using long, impossible-to-remember strings of numbers. We use names: youtube.com, amazon.com, wikipedia.org. Somewhere, there has to be a system that translates these human-readable names into the machine-readable IP addresses that the network actually runs on. It's the internet's equivalent of a phone book, but it's a phone book of unimaginable scale, speed, and importance. And without it, the entire user-friendly web as we know it would simply cease to exist. So now we have the address. The domain name system has done its job, translating a human-readable name like youtube.com into a string of numbers, an IP address that a computer can understand. But an address is just a destination. The real question, the one that defines the modern world, is how do you get there? How does your request, a tiny packet of data born in your living room, travel thousands of miles in the blink of an eye to a server on another continent and get a response back before your brain can even register the delay? The answer isn't in the sky. It isn't in satellites or Wi-Fi beams crisscrossing the globe. The popular image of the cloud is a comforting ethereal lie. The internet is not a cloud. The internet is in the ocean. Over 99% of all international data is transmitted through a vast, sprawling network of fiber optic cables laid on the ocean floor. We're talking about more than 800,000 miles of cable, enough to wrap around the Earth more than 30 times. This is the true backbone of the internet. A physical, tangible thing you could hold in your hand. These cables are the arteries of our global civilization, pumping the lifeblood of data, your emails, your video calls, your bank transactions, this very video, at nearly the speed of light. So what is one of these cables, really? If you were to see one up close, it might seem underwhelming. The entire cable is often no thicker than a garden hose. But inside that protective sheath of plastic, steel wire, and copper is a core of optical fibers, each one as thin as a human hair. And through these impossibly thin strands of pure glass, information travels not as electricity, but as light. Your data is converted into billions of pulses of laser light per second. Each pulse is a 1, each absence of a pulse is a 0. These light pulses race down the glass fiber, bouncing off the inner walls in a process called total internal reflection, losing almost no energy along the way. It's a system of such staggering elegance and efficiency that a single fiber can carry tens of terabits per second. That's enough bandwidth to transmit several million high-definition movies simultaneously. And a modern subsea cable contains dozens of these fibers. Laying these cables is a monumental feat of engineering. Specialized ships costing hundreds of millions of dollars slowly unspool the cable onto the seabed, sometimes miles deep. In shallower waters, an underwater plow is used to bury the cable under the sand to protect it from ship anchors and fishing trawlers, which are, by far, the biggest threats to the network. And yes, in the early days, sharks did occasionally bite the cables, seemingly attracted to the electromagnetic fields from the high-voltage power lines that run alongside the fibers to power the amplifiers. Modern cables are much better protected. Every 40 to 50 miles along the cable, there's a repeater, a device that acts like a tiny signal booster. It takes in the faint light signal, which has weakened slightly over its journey, converts it to an electrical signal, amplifies it, and then turns it back into a fresh, strong pulse of light to continue its journey. These repeaters are powered by that copper sheath, carrying thousands of volts from landing stations on either end of the continent. So let's follow your data packet. You click on a video, DNS finds the IP address. Your computer fires that request, encoded as light, out of your house, through your local ISP's network, and it arrives at what's called a cable landing station. This is a nondescript, highly secure building on the coast, the gateway where the terrestrial internet meets the global subsea network. Your packet, now just a flicker of light, plunges into the Atlantic or Pacific Ocean. It travels for thousands of miles in a few dozen milliseconds, crossing underwater mountain ranges and abyssal plains. It surfaces at another landing station, say on the coast of France. But its journey isn't over. It hasn't reached the YouTube server yet. Now, it has to navigate the terrestrial internet of another continent. And to do that, it enters one of the most important and least understood pieces of internet infrastructure: the Internet Exchange Point, or IXP. Think of an IXP as one of the world's busiest airports, but for data. It's a massive data center, a physical building where hundreds, sometimes thousands of different networks all converge. We're talking about internet service providers like Comcast and Verizon, content delivery networks like Akamai and Cloudflare, and content giants like Google, Meta, and Netflix. They all bring their infrastructure, their routers and switches, into this one neutral building. Why? To exchange traffic directly. It's a process called peering. Instead of Google paying a third-party telecom company to carry its YouTube traffic to a Comcast customer, Google and Comcast can agree to connect their networks directly inside an IXP and exchange that traffic for free, or for a much lower cost. It's like two airlines agreeing to let their passengers transfer between their gates at an airport without having to go back out through security. This is the secret to a fast, efficient internet. By peering at an IXP, data can take the most direct route possible from one network to another. Your packet, having just arrived from America, might enter an IXP in Frankfurt, Germany. Inside, it zips across a connection from the transatlantic cable operator's network directly onto Google's private network. It's a handshake that happens in nanoseconds. There's no middleman, no scenic route through another country's network. It's the ultimate shortcut. These IXPs are the hidden hubs of the digital world, Places like the Equinix Ashburn campus in Virginia, often called Data Center Alley, handle a massive percentage of the entire world's internet traffic. They are some of the most critical, yet anonymous buildings on the planet. From the IXP, your packet is now on Google's private global network. A network so vast it's a Tier 1 internet backbone in its own right. It travels along their own fiber optic lines to the specific data center, one of thousands, that holds the video you requested. Once it arrives, the server processes the request, finds the video data, and sends a stream of new packets on the return journey. Those packets containing the video race back through Google's network, back to the IXP, back to the subsea cable, back across the ocean floor at the speed of light, back to the landing station on your continent, back through your ISP's network, and finally arrive at your router, your computer, your screen. And all of this, the lookup, the journey across the ocean, the handshake at the IXP, the trip to the data center, and the entire return trip, happens in less than 200 milliseconds. Faster than you can blink. Faster than a nerve impulse can travel from your finger to your brain. This is the physical reality of the modern world. It's not a cloud, it's a colossal machine of glass and light, of ships and plows, of anonymous buildings and deep-sea repeaters. We have wrapped our planet in a web of our own making, a nervous system for humanity. But this incredible system, this foundation of our global economy and society, is also incredibly fragile. A single ship anchor in the wrong place can sever a connection between continents. A geopolitical dispute can determine who gets to tap into these data streams. The physical layer of the internet is not just a technical marvel. It is a new landscape for power, control, and conflict. Because when you control the cables, you control the flow of information itself. And that brings us to the very top of our stack, to the silent, invisible battles being fought every single day to secure, control, and dominate this global network we all depend on. This digital frontier, this global nervous system we've spent this entire series mapping, is not a peaceful utopia. It is the newest and most consequential battlefield in human history. The conflicts fought here are largely invisible, waged in microseconds across fiber optic lines, and through the silent logic of code. The weapons are not bombs and bullets, but malicious packets, zero-day exploits, and sophisticated algorithms designed to disrupt, deceive, and dominate. One of the most common forms of attack is brutally simple in its concept: the distributed denial of service or DDoS attack. Imagine you're trying to get into a single store, but a million people, a botnet of compromised computers, are all instructed to crowd the entrance at the exact same moment. No one can get in, no one can get out. The store is effectively shut down. In the digital world, this means flooding a server, a website, a banking system, an entire nation's online infrastructure, with so much junk traffic that it collapses under the strain. It's not about stealing information. It's about silencing a voice. It's about making a service, an idea, or a government simply unavailable. This is a direct assault on the fundamental promise of the network: its availability. But silence is just one objective. The real prize is the data itself. Every packet we've talked about zipping across the globe is a potential target. Governments and intelligence agencies have invested billions in creating listening posts, not in the traditional sense, but by tapping directly into the massive data centers and submarine cable landing stations we explored earlier. They siphon off colossal amounts of information, looking for patterns, for secrets, for leverage. This is where encryption becomes so critical. It's the digital armor for our data packets, a complex mathematical shield that turns our private messages and financial transactions into gibberish for anyone without the key. The battle then becomes a perpetual arms race between the codemakers and the codebreakers, a high-stakes cryptographic war that underpins global security. And some nations have taken control to its ultimate conclusion. They haven't just tapped the network, they have fundamentally reshaped it within their borders. The most famous example is the Great Firewall of China. It is not just a simple list of blocked websites. It is a sophisticated, multi-layered system of control that operates at every level of the network stack. It uses DNS poisoning to send you to the wrong address, packet filtering to inspect the data you're sending and receiving, and deep packet inspection to actively terminate connections it deems undesirable. It creates a completely separate, curated, and monitored version of the internet, a digital territory with hard borders, a stark contrast to the open, borderless frontier the internet was envisioned to be. It's a powerful demonstration that the architecture of a network directly reflects the political ideology of its creators. Yet, nation-states are no longer the only superpowers in this domain. A new set of empires has emerged, not defined by land or military might, but by data and infrastructure. I'm talking about the tech giants, Google, Amazon, Microsoft, Meta. These companies are not merely on the internet. In many ways, they are the internet. Think about it. Amazon Web Services, or AWS, hosts a staggering portion of the entire internet. Countless websites, applications, and even government agencies run on Amazon's servers. Google doesn't just index the web. It handles the majority of the world's searches, provides its most popular email service, its dominant mobile operating system, and its largest video platform. Meta doesn't just run a social network. It has created a global communication fabric connecting billions of people. These companies own the data centers. They lease the transoceanic cables. They operate the massive content delivery networks that make our streaming services and websites load instantly. They have become the de facto infrastructure of modern life. They are digital continents with their own rules, their own economies, their own populations, and their own form of governance, dictated by terms of service and community guidelines. The decisions made in boardrooms in Silicon Valley can have a more immediate impact on free speech and the flow of information than laws passed in Washington, D.C. They can deplatform a world leader, change the algorithm that determines what news a billion people see, or alter the economic reality for millions of small businesses overnight. This is an unprecedented concentration of power, a centralization of a system that was, by its very nature, designed to be decentralized. And that brings this entire journey from the physical cable to the geopolitical battlefield right back to you, to us. Every time you use a free service, you're not the customer. You are the product. Your data, your clicks, your likes, your searches, your location is the currency. It's the raw material that fuels the multi-trillion-dollar engine of targeted advertising and machine learning algorithms. We have willingly, often unknowingly, entered into a grand bargain. Our privacy in exchange for convenience. We've traded autonomy for an ecosystem that knows what we want before we do. This growing unease with centralized control has sparked a powerful counter-movement. You may have heard the buzzwords. Web3, the decentralized web, blockchain. At their core, these are not just new technologies, they are a philosophical rebellion. They represent an attempt to re-decentralize the internet, to snatch power back from the hands of a few giant corporations and governments and distribute it back to the users. The idea is to build systems where data isn't stored in a central server owned by a single company, but distributed across a network of thousands of computers, where your identity isn't tied to a Google or Facebook account, but to a cryptographic key that you, and only you, control. It's an ambitious, messy, and uncertain effort to return to the internet's peer-to-peer roots, to build a network that is inherently more resilient, more private, and more resistant to censorship. And so, we arrive at the very top of the stack. We've journeyed through all 7 layers of the OSI model, from the physical electricity in the wires to the applications on our screens. But there is an 8th layer, an unofficial one that is arguably the most important of all, the human layer. Because this network, this incredible world-spanning machine of unimaginable complexity, is ultimately nothing more than a reflection of us. It reflects our brilliance, our creativity, our desire to connect and share. It also reflects our greed, our tribalism, and our capacity for conflict. The technology is neutral. The protocols, TCP, IP, HTTP, DNS, they don't have an agenda. They are just incredibly efficient tools for moving bits from one place to another. We are the ones who imbue it with purpose. We are the ones who choose to build bridges or walls. We are the ones who spread knowledge or misinformation. We are the ones who foster community or sow division. The story of computer networking is not just a story about technology. It's the story of modern civilization. It's a story of how we chose to connect ourselves, wiring our economies, our politics, and our very consciousness together into a single, intricate, and fragile web. The challenges we face now, of privacy, of security, of truth itself, are not technical problems seeking a technical solution. They are human problems. The future of this network is not pre-written in code. It is being written every day by every one of us. By the engineers who design more secure systems, by the policymakers who grapple with its regulation, and by every single person who chooses what to click, what to share, and how to engage in this global conversation. The most important protocol isn't a technical standard. It's a social one. It's empathy. It's critical thinking. It's the shared responsibility to be good stewards of the most powerful communication tool humanity has ever invented. The real deep dive isn't just into how the modern world is connected, but into the kind of connected world we truly want to build.